Welcome to the Rotary Wing Case Study Part 2. In Part 1 of the Rotary Wing Case Study, we talked about how to control a microaerial vehicle. In this second part, we talk about how to make these autonomous robots that are able to perform tasks without explicit human intervention. To do so, at least two more big modules are necessary. The first one is the perception module that is responsible for state estimation and environmental mapping. The second one is the planning module, which plans feasible paths such that the vehicle is not endangered and can fulfill its mission. First, we will talk about the perception module. So, what is special about perception on microaerial vehicles? The perception requirements for an MAV can roughly be structured into three main goals. The first one is state estimation, which is the process that deals with estimating our current position, orientation, velocity, and so on. Basically everything that we need to control the system. Therefore, the output of the state estimation system is directly fed into the controller and should come at a suitable frame rate, which usually is on the order of 50 to 200 Hz. The second biggest task is mapping. Mapping deals with perceiving and establishing a map of the physical world such that the MAV is able to plan feasible paths and goal fulfillment paths in its environment. The last task, localization, deals with combining state estimation and mapping and gives us an absolute reference with respect to a given map at usually a few hertz. This task is rather computationally expensive, therefore it is not run at the same frequency as state estimation. In the following, we will give you a short overview of the typical sensors used for perception navigation on MAVs. One of the most important sensors on a flying vehicle is the inertial measurement unit, short IMU, which usually consists of 3 accelerometers and 3 gyroscopes that measure linear acceleration and rotational velocities. This is a sensor that gives us very, very high frequency data up to a few kilohertz and senses the forces and rotations that are acting on the body directly. Often we also have cameras on the system to be able to visually perceive the environment. Depending on the use case, this can be high-frequency mono cameras, stereo pairs, and depth cameras. More and more, LiDARs are a feasible alternative for sensing on MAVs. 10 years ago, LiDARs were usually too big and too heavy and too expensive to mount them on a flying vehicle. Nowadays, there are LiDARs like the Auster OS1, for example, that are in the range of a few hundred grams and are as such feasible to be flown with a drone. While flying outdoors, GPS is one of the most important sensors because it gives us an absolute reference with respect to a fixed world frame. Recently, there are also feasible differential and RTK GPS systems available on the market that, given a base station, can give us up to centimeter precision at around 10 Hz. While flying outdoors, a magnetometer can be used as well, which is nothing else than a digital compass. However, magnetometers are very sensitive to stray-induced currents from the motors and to the environment. So usually they're only accurate to about 2 degrees roughly. If flying at very high altitude or big altitude range, a barometer, a pressure sensor, can also be quite useful to estimate the current altitude in the atmosphere. There are a few reasons why perception on MAVs is especially challenging. The first reason is limited computational power. Because processing should happen online for delay reasons and communication reasons, we are bound to whatever computer we can fly on the system. Currently, our computers are usually in the range of about an i7 processor with an SSD and few gigabytes of RAM. However, to fly GPUs nowadays is quite difficult, so many learning-based methods are still not used that much in flying vehicles, but there are small boards that give you part of the performance of a GPU like the NVIDIA Jetson. Another reason, of course, is the limited payload. The typical flying MAV is quite light, on the orders of a few kilograms, and you can't just put as many computers or as many sensors you want onto the system. Another big problem or limitation is the limited sensor quality, because usually quite lightweight sensors are used. For example, cameras can't have big lenses because of the weight and the size. We deal with sensors that are not perfect. So there is noise and there is aliasing. And of course, compared to a ground vehicle, MAVs are able to perform really, really fast and dynamic maneuvers, which makes perception really challenging because things like motion blur affect us way more than on a slow ground robot. And lastly, unlike ground robots, MAVs operate in 3D space, so we don't have any prior about that we're on the ground or that we have wheels that don't slip, for example. To visualize this a bit, these are two examples of a fully integrated, fully autonomous system that were used in a robotic challenge. These systems are on the order of a few 10 centimeters wide, and you see there are many sensors integrated in a very, very tight space. And because of weight restrictions, a lot of sensors, for example, don't have a case or don't have protective cases. So it's also you have to operate these machines very carefully. Here is a close-up of one of the sensor systems on one of the drones. So what you can see here is a stereo camera, the calibrated stereo pair that gives us stereo features at 20 Hertz, and an IMU that runs at about 200 Hertz. In the following, we'll have a closer look at the state estimation problem. So in a perfect world, you could just integrate accelerometer data, meaning accelerations and rotation velocities from the IMU, and obtain your velocity, integrate again, and obtain your position. The problem is this is not feasible. IMU have biases, meaning non-zero mean noise. These biases can be dependent on temperature, voltage level, mechanical noise, and so on. Those usually have to be estimated together with a different sensor to make the IMU useful. The IMU alone, if you would do this, this state estimation would drift largely, because all the error that you integrate up leads into wrong velocity estimates. Wrong velocity estimates integrated again leads to very, very wrong position estimates. Usually you can only fly a few seconds with the IMU only before it drifts into oblivion. So the main idea of state estimation on MAVs is to combine the IMU with a sensor that does not drift, at least does not drift locally. The reason why there still is an IMU because we need the high frequency data of the IMU to obtain a smooth and high frequent state estimation. Common solutions of combinations with IMUs are IMU plus GPS. This is sort of the default solution for outdoor flying, and most commercial drones that are easily obtainable off the shelf use some sort of IMU and GPS fusion. For indoor flights, we often use visual inertial odometry. Here we combine IMU with the appearance feature tracking from a camera. A rather newer variant is LiDAR inertial odometry, where we combine IMU data with geometric tracking and localization from a 3D LiDAR. In the following, we'll have a closer look at two different visual inertial odometry algorithms. The first one is a Kalman filter-based approach called ROVIO. In this Kalman filter-based approach, we perform a prediction using an IMU to forward predict our current state, and then use a pixel intensity error to update our state. In the pixel intensity error, different image patches are compared based on their forward prediction, and the error in their photometric difference is minimized. This is quite robust against aggressive motion in the illumination change. It is robust against aggressive motion because it uses the high frequent IMU to forward predict where the features will lie in the next frame, and it uses this patch intensity error, which is quite robust against illumination change compared to some of the feature methods that are in literature. It's computationally very efficient because we don't have to perform any optimization as such. Because it's a local approach, there is no fixed map. It only tracks the features that are visible from one frame to the other and forgets all features to be computationally efficient. It still accumulates drift over time, but orders of magnitude less than just predicting the IMU. Usually on a trajectory of 100 meters, this may accumulate on the order of 10 centimeters to half a meter of drift, depending on the features that are visible, depending on the aggressiveness of the motions, and depending on the lightning. And also, of course, depending on the camera and IMU quality. The approach is published in the paper cited below, and there is also an open source implementation which you can find on our GitHub, and that is widely used in different labs around the world. This slide illustrates what happens in a Kalman filter-based visual inertial odometry method. On the left side, you can see an illustration of a state in a 2D world, XD, the black dot, and its associated covariance, PT, the gray ellipsoid. By doing a prediction step with an IMU, the position moves according to the accelerations and rotations felt by the IMU, and the covariance grows because we tuned the system to associate a higher covariance to the IMU data. If we would only update these steps and reiterate using the IMU, the covariance would grow unbounded. That means at some point we don't know anything about our state anymore, which also reflects a bit what actually happens if you forward predict using an IMU only. To alleviate that and to shrink the covariance, we use the aforementioned image patch update that is associated with a lower covariance because the camera gives us a very fine-grained information about the angle under which we see an image patch. The state moves according to the patches, and also the covariance grows according to the covariance associated with the camera update. By performing these steps iteratively, we obtain a relatively drift-free estimate compared to using the IMU only, and most importantly, we can keep the covariance of our state bounded, which also means we always have a somewhat reasonable estimate of our current position. This is a video of the system as it works on a real drone. The green frames you can see are the tracked image patches, and sometimes on some patches you may see a yellow ellipsoid. This is the covariance associated with that patch at the moment of the frame. Even for somewhat dynamic movements, the system still can keep up with tracking the image patches because the IMU allows us to forward predict where to look for a specific patch in the next frame. Even in high rotational movements, which lead to very high displacement of the image patches in the image plane, the system is able to keep up with the movement of the MAV and accurately gives us a state estimation, which is visualized in the top right corner in 3D space. A different approach to visual inertial odometry is to use a graph-based optimization algorithm instead of a Kalman filter. In such a keyframe or graph-based approach, we extract features from frames, triangulate them, and match them between different frames. Because we cannot keep all of the features and all of the frames in our optimization solution, because it would be too expensive to compute, the system defines keyframes and optimizes between these keyframes. As stated, it is an optimization-based method. That means there is some algorithm that runs a mathematical optimization, which can take a lot of CPU processing. It accumulates less drift over time because the system is more constrained and the optimization leads to a bit more accurate results. But as said, it's computationally expensive, but nonetheless feasible to be run on a standard MAV. If you're interested, the citation at the bottom gives you a very complete overview of the system explained here. To give you some intuition of what actually happens in this graph-based optimization method, we'll use a graphical scheme to visualize the data. Here on top, the many landmarks, this is basically a sort of a map. So landmarks, features that we keep. The green squares are feature measurements, which are connected to a specific pose. So that means the gray circle is a pose, some position orientation, under which we made the green observations of the landmarks. This slide provides a visualization of what actually is optimized if we see the same landmarks on different frames at different poses. So the three stars visualize landmarks in 3D space, which are then perceived by a camera at a pose at time equals 1 to obtain the image as seen on the screen, which of course is the rays that come from the landmarks and pass through the image frame, which leads to this image. If we now move the camera to a different position at t equals 2, we obtain the same landmarks at different locations on the frame. But of course, because we don't know exactly how the camera moved, we might only have a prior, there is some error, which is indicated by the non-filled stars here. And the actual error between the actual observation and the hypothesized observation is indicated by the red arrows. So the question now is, given this situation, how do we have to change our belief about the state at t equals 2 to make these features match their observation? Which is in the scheme as seen before visualized like this. So now we have two observations with key point measurements. And the optimization happens between those two poses. But because we also want to have a prior to make the optimization faster and to also have a higher update rate between poses, we include IMU measurements between the subsequent poses, which then leads us to a situation like this, where we actually have an IMU constraint that gives you the range of all feasible camera locations that could have led to the image seen on the screen. Going back to the illustration of the algorithm, we can now formalize the optimization problem. So we have a bunch of poses, the gray circles, that are connected by IMU measurements, meaning there is always a relative measurement between two poses that we observed using the IMU. But at the same time, each pose has an associated set of key point measurements. And of course, the discrepancy between the actual pose and how much error we saw with respect to the relative IMU measurement or with respect to where we should have observed the key points are our error terms. These we can optimize by changing the poses in the optimizers so that we obtain a trajectory that minimizes all the error over all the observations that we connected in this scheme. If we find a trajectory that minimizes these error terms, we can conclude that this is the set of poses that explains our data the best and thus is the most likely trajectory that the MAV has performed. And of course, the set of landmarks can be interpreted as some sort of map, because we start to obtain a set of observations about the real world and use them to localize against. Such a map can look something like this. This is from a handheld data set done in the MapLab paper, which is also an open source software for performing map-based localization and mapping, where we see all the colorful dots are individual landmarks, and we see in the middle an example of one observation that is connected to all the landmarks observed. And by doing multiple trajectories through this building and co-optimizing everything together, we obtain a nice, consistent, and also geometrically accurate representation of this building in terms of features. Below you can see an overlay of the feature map onto the building plan, which shows a very high consistency. This leads us to the next big topic in perception for MAVs, which is mapping. So what problem are we trying to solve with the mapping process? We want to acquire a model of the physical environment from a moving robot, such that the robot can use the model to plan future movement, future trajectories, and can also localize itself against the map, so it knows where it is with respect to the map. One key design criteria for building a mapping system is the map representation. Depending on what types of tasks we want to use the map for, we might choose a very different map representation. Typical map representations used are, for example, topological maps that only connect places and give us information about how to get from one place to the other without necessarily respecting the physical realities. Another type of map that is often used are volumetric maps, which gives us a 3D information about free versus occupied space. For surface-based operations such as spraying, painting, or following surfaces, meshes are often used. And for human-centric tasks and more also in robotics, semantic maps are used that are giving us information about the type of an environment. For example, here we see different types of surface, lake, civilization, land marked. But as always, it highly depends on the use case. One key takeaway here is that the mapping representation should fit the planning algorithm, vice versa. This is quite obvious, as it's really hard to plan for obstacle avoidance, for example, in a topological map, whereas this is really easy to do in a volumetric map. One of the simplest type of volumetric map representation is the so-called occupancy grid mapping. By doing so, we divide the 2D or 3D space. Here it's an example in 2D, but of course it's the same thing in 3D. So we divide the 2D space into equally sized boxes, of which we keep track whether they are occupied, free, or unknown. So in this example, we have this blue-shaped obstacle in the middle, and all the white boxes are still unknown. Now, if you have some sort of sensor, for example, a laser that provides us 1 point, or a stereo camera that provides us thousands of points, or a LiDAR, we can start to keep the map accurate and up to date. So by having this laser ray that goes through the map and reflects the obstacle at a certain distance, we know that everything, all the boxes up to the obstacles must be free, and the box where we actually have the laser measurement from is occupied space. By doing this iteratively and while the robot moves in the world, we can keep on updating the map and at some point obtain a globally consistent map about where we can fly through and where there are obstacles. The approach is not without its issues because we discretize the space. It can also happen that we pass through a box without seeing the obstacles and then subsequently mark the box free, and then in the next path it's occupied again. So what are the issues with such a naive occupancy grid? As mentioned before, it usually has a fixed resolution, meaning that it's either very coarse, as seen before, and you have problems with having boxes that contain free space and occupied space, or it can become very memory efficient if you have a very high resolution, a very large workspace to cover. They do not account for sensor noise, so there is no notion of covariance about the belief state of a specific location in the map. It's usually just these three categories as mentioned before: occupied, free, unknown. But most importantly, there is no gradient for planning. Let's say we want to plan a path and we see in the map that it leads through an obstacle. Which way do we need to adjust our plan so that we are out of the obstacles with the least deviation to the original plan? A very famous implementation of such an occupancy grid is called Octomap. It's a bit more efficient than just storing it in a three-dimensional grid because the grid is subdivided into trees. They're called octrees, which basically only assign data to space we have seen. So a 3D space does not need to be fully assigned. It also uses a probabilistic occupancy estimation, which helps us in case of sensor noise or inaccuracies in our state estimation. And it's also able to model free, occupied, and unknown space. Because it only assigns memory for spaces that we have data for in this tree, it's somewhat more memory efficient for a large-scale environment. But it also assumes a known robot pose, so it does not solve the problem of localization. On the bottom right, you see a typical map, how it is visualized in ROS. Of course, as you can see, this map looks very, very perfect and has probably been done in some simulation. If you're interested, the citations at the bottom of the slide. Also, Octomap is open source and can just be downloaded and tried out. To solve the aforementioned problem of not having a gradient called collision gradient in the map to change our trajectories if they go through obstacles, we can store the distance to the next occupied cell in the grid. This representation is called a signed distance field. To illustrate it, we have the same obstacle situation as before, and instead of just keeping occupied unknown free, for all the free cells we keep the distance to the obstacle in the cell. A well-known implementation of such a signed distance field is VoxBlocks. It is a volumetric mapping library that runs real-time on board using just the CPU, and it constructs the occupancy grid and the distance field simultaneously. See the paper if you are interested in this. Paper is cited below, and on the right side you can see an illustration of how such a signed distance field looks in real life. The following I'll show you the video of the system. So here we see a drone taking off, and on the bottom left you can see the current belief state of the map given the integration of the sensor data from the stereo camera pair on board of the drone. As you can see, the map is dynamically updated while we move in the world. This leads us to the next topic, planning for microaerial vehicles. So, as shown in the beginning of the perception part, here we are again with the different parts to make a MAV autonomous. We already covered the control part and the perception part, and now the last part, the planning part, is responsible for generating paths for the robot to execute a desired mission. So what is actually motion planning? In the motion planning problem, we try to compute a continuous sequence of collision-free robot configuration that connect a desired initial and goal configuration. So the input is, of course, a initial and goal configuration, which can, for example, be the start and end of a maze or the start and end of some sort of task. We have an environment model, the map, and we know something about the robot kinematics and geometry. We have, for example, need to know the size of the robot so that we can plan collision-free paths. The output is a success or fail notion, because in some maps and for some start and goal configurations, either the map might forbid that we find a feasible path because there might be no connection, or the robot kinematics might also tell us that, for example, we want to move too fast or to a state that is impossible for the system. But in case the planning is successful, it outputs a collision-free path from initial to goal configuration as visualized in this image on the right. One famous algorithm is called jump. The way it works is we have a signed distance field as explained before. First, we plan just a direct path from goal to start as if we wouldn't know anything about the map. But then for each control point in the path, we check if it's part of an obstacle. And if so, we move them along the collision gradient, meaning from here in this image, from red regions towards greener regions, which gives us something like this. We then also optimize for smoothness and obtain a new path. Sometimes this doesn't lead directly to collision-free paths, so we iterate this until we are happy with our path. This is a visualization of the algorithm in a artificially generated map. You'll find the citation of the algorithm at the bottom of the slides if you're interested. So as you see, it optimizes very quickly to have almost a collision-free path, and then in some edges sometimes needs a bit more iterations, but finally ends up with a path that tries to be away from the obstacles as much as possible. Here we see a video of a live system that performs trajectory optimization and collision avoidance based on an onboard map. First, the MAV starts on the right side and has to plan a path to the goal that actually lies inside the obstacle on the left side. To go there, it first has to plan a path around the mattress obstacle and then tries to get as close as possible to the goal position, but decides not to reach it because it actually is inside an obstacle and dangerous. Here we see the map as it is being built on board. We see that according to the map state, the trajectory is optimized on the fly, and the MAV always looks for a feasible and smooth trajectory that does not interfere with obstacles. By showing the system on a large-scale simulated forest, we can see that the trajectory optimization method is able to also generate collision-free paths in more complex environment, and that is also able to seamlessly replan while it obtains new information about the world. With a system like this, it is possible to fly to dense and cluttered environment without risking a crash with the environment. This concludes the second part of the rotary wing case study. I hope it was interesting and gave you some insight in how perception and planning is performed on board MAVs. If you want more information or are interested in student projects, check out our website and our YouTube channel.